Hey, mathletes. Welcome to the video where we're going to start talking about the derivatives of exponential functions. So if we've explored limits, derivatives are the next place we go. Just a quick reminder that when we are finding derivatives, what you're finding is the slope of the tangent line or the instantaneous rate of change, okay? We haven't talked about that much when sometimes we forget about it, I guess, when we're just finding all these derivatives rules. So just think about that. Okay, so what we're going to look at here is the most kind of special exponential function that we're going to see, okay, in math. So first off, we need to learn something new. We're going to talk about a very, very special number in math. Like 0 is a special number in math, and 1 is a special number, and pi is a special number. But a really, really special number that most people don't see until maybe they get to calculus is e. Okay, now you can go and find E on your calculator. It's usually somewhere around your log button, and there's a reason for that. E is a very special irrational number that is approximately this. And it keeps going forever because it's irrational, okay? E is named after Euler, okay, but not like the Edmonton Oilers, this Euler, who was a famous mathematician way back in the day. And E is one of these numbers that appears in nature, okay, and a lot in nature, a creepy amount in nature. So what I need you to know about E is it allows us to have continual growth. What's he talking about? Well, when you were looking at exponentials, maybe in a different class, whenever you drew an exponential of something growing, so say it was bacteria growing and you drew it as if it was continual growth. But if you wrote it like something like this, here's a bacteria and it's doubling every day. Well, every day, n is an element of the whole numbers then, or the naturals. So if you actually thought about this, you wouldn't draw a continual growth. It would actually be a discrete graph. So what E does for us, without getting too wildly crazy into it, what E does for us is it allows us to find continual growth, so instantaneous growth, okay? So E is a very special number is what I'm trying to get at. It has all sorts of applications. We see it in business and finance for investing money, population growth curves, all sorts of things, okay? So E, it's your new special number if you've never seen it before. That's what we're going to look at today, the derivative of e to the fx. Well, I've got great news for you. It is the easiest derivative you're going to learn all year. The derivative of e to the x. You ready for this? The best derivative ever is just e to the x. Okay, that's why this function's so cool. The derivative of e to some exponent that's a function, well, we're going to use chain rule then. E to the fx times f prime at x. Okay, so there's your fancy new rule for this fancy new value e. All right, so let's take some derivatives. These are the easiest derivatives all year. So take the derivative of y is equal to e to the 2x. Okay, so they ask us to write it in this formation, or this notation, I should say, Leibniz notation. Well, the derivative of e to the 2x is e to the 2x times the derivative of the exponent, which is 2. And all I would do at that point is just bring that coefficient out front. Isn't that super cool? Okay, try another one. All right, well, we got e to the x to the 1/2. So dy dx, change in y with respect to the change in x, is e root x. Okay, chain rule, the derivative of the exponent then would be 1/2 x to the negative 1/2. And the derivative of 1 is just 0. And then all I would like you to do is rewrite that with non-negative exponents, just like that. There it is. Okay, so again, it's such a nice function to take a derivative of. Okay. Now, like I was saying, when we're taking derivatives, don't forget we're finding the slopes of the tangent lines, which is giving us that instantaneous rate of change. So let's try one of these. Determine the slope of the tangent to the curve y is equal to e sine 2x when x is pi over 2. Okay, if we want the slope, what we're going to do, slope is equal to the derivative of this thing. So we take the derivative, e sine 2x. All right, well, now we got to remember the derivative of sine. Well, the derivative of sine is cos 2x, and chain rule one more time, times 2. So that's the equation of all the slopes of the tangent lines for all values of x. Well, we want the slope when x is equal to pi over 2. So we want the slope when x is equal to pi over 2. So we go and we sub in pi over 2 everywhere. Okay, we sub in pi over 2 everywhere. Hey, maybe we need those exact values from our unit circle. Hey, that's a good thing, right? That's why we need to know that. So x pi over 2. Okay, so now we've got e. Well, those 2's divide out. These 2's also divide out. So we got sine at pi. Sine at pi, if you remember, is the y value. Here, I'm even going to draw a sketch. Right here. There's pi. That's the coordinate -1, 0. And sine is your y value. So this is simply 0. Sine at pi is 0. Times cos at pi. Well, cos at pi is the x value. So the x coordinate at pi right here is -1 times 2. Well, guess what? What's our slope then? Our slope when x is equal to pi half. Well, that's e to the exponent of 0 is 1. So we got 1 times -1 times 2. That sounds like -2. So our slope is -2. And that's what we just found. Determine the slope of the tangent to the curve. There it is. The slope at that moment is -2. So again, all I need you to know about E for now is E is an incredibly special number that allows us to work with functions in a continual growth. It is so important. It's a million times more important than pi. Okay, shows up in nature everywhere. We're going to see it again when we talk about logarithms. So this will come again. Okay, friends, there is the derivative of e to the x, a very special exponential function.